This is a video from section 7.8. The directions say to determine whether the integral is convergent or divergent. Evaluate integrals that are convergent. So we're going to go ahead and start with example 1. Suppose I have the integral from 1 to infinity of 2x to the negative 3 dx. So this is the limit as t goes to infinity of the integral from 1 to t of 2x to the negative 3 dx. And so this is the limit as t goes to infinity, and, well, we integrate in the typical way, so this is going to be 2x, negative 3 plus 1 is negative 2, so 2x to the negative 2 divided by negative 2. And we're going to evaluate from 1 up to t. So this is the limit as t goes to infinity. Notice I have not taken a limit yet. And so this is negative x to the negative 2 from 1 to t. So the 2's cancel. And so this is the limit as t goes to infinity. I'm going to plug t in for x. And I'm going to get negative t to the negative 2. And I'm going to plug 1 in for x, and I get minus a negative 1. Okay? And so this is the limit as t goes to infinity of 1 minus 1 over t squared. And so as t gets large, the second term goes to 0. And so the answer is 1. And so what we can say is the integral from 1 to infinity of 2x to the negative 3 dx converges. That's how you do example 1. Let's take a look at example 2. Suppose I had the integral of 1 over cube root of x dx, and we're going to go from negative infinity up to negative 1. And so this is the limit as t goes to negative infinity of the integral from t to 1 of, if you don't mind, I'm going to write this as x to the negative a third dx. So this is the limit as t goes to negative infinity of. Now, if I add 1 to that negative 1/3 exponent, I get 2/3. But I'm supposed to divide by 2/3, but that's the same as multiplying by 3/2, right? That's how you do a typical integral. And we're just going to evaluate from t up to 1. So this is the limit as t goes to negative infinity of, now plug 1 in for x, you get 3/2. Plug t in for x, you get 3/2 t to the 2/3, like so. Now, when I let t go to negative infinity, the cube root of negative infinity, quote unquote, is negative infinity, and if I square it, I get infinity. So the answer here is negative infinity. And what that tells me is that the integral from negative infinity to negative 1 of 1 over the cube root of x dx diverges. Let's take a look at example 3. Suppose I have the integral from 1 to infinity of 1 over x squared plus 4 dx. So this is the limit as t goes to infinity of the integral from 1 to t of 1 over x squared plus 4 dx. And so this is the limit as t goes to infinity of, now I'm integrating basically 1 over x squared plus a squared, where a is 2. So I'm going to get 1 over a, which is 2, arctangent of x over a, where a is 2, and I'm going to go from 1 to t. If I plug the t in for x, I get the limit as t goes to infinity of 1/2 arctangent of t over 2 minus 1/2 arctangent of a half. And so when I let t go large, I get 1/2 times pi over 2 minus 1/2 arctangent of a half. But this is pi over 4 minus 1/2 arctangent of a half. And so what that tells me is that the integral from 1 to infinity of 1 over x squared plus 4 dx diverges. And that's how you do example 3. So let's go ahead and take a look at example 4. Suppose I give you the following. Suppose I give you the integral from 0 to infinity of 1 over the 4th root of 1 plus x dx. This is equal to the limit as t goes to infinity of the integral from 0 to t of, if you don't mind, I'm going to write this as x plus 1 to the negative 1/4 dx. Now, this is a typical integral, so we get the limit as t goes to infinity of, now if I take 1 and add it to negative 1/4, I get 3/4. But I have to divide by 3/4, which is like multiplying by 4/3. So I get 4/3 of x plus 1 to the 3/4 evaluated from 0 to t. And so this is the limit. I have not taken a limit. I haven't even attempted it yet. When I plug t in for x, I get 4/3 times t plus 1 to the 3/4. When I plug 0 in for x, I get 4/3. When t gets large, this is going to be infinity. And so what that tells me, the integral from 0 to infinity of 1 over the 4th root of x plus 1 dx diverges. So we're getting a good mix of converge and diverge. Let's go ahead and do another one. Suppose I give you this one. We'll call this example 5. Suppose I had the integral of from 2 to infinity of x divided by the square root of x squared minus 1 dx. This is the limit as t goes to infinity of the integral from 2 to t of x over the square root of x squared minus 1 dx. So this is the limit as t goes to infinity. Now, notice that the derivative of x squared minus 1 is 2x, but I'm missing a 2. So when I integrate this guy, I'm going to get square root of x squared minus 1. And I'm going to go from 2 up to t. Because, we can come over here for a second. So if I have x over the square root of x squared minus 1 dx, so I'm going to let u be x squared minus 1. du is 2x dx. So x dx is 1/2 du. And so this is 1/2 the integral of 1 over the square root of u du. But this is 1/2 of, I claim this is 2 square root of u plus c. But u is x squared minus 1. So the 2's cancel, and you get the square root of x squared minus 1 plus c. So that's how you take the antiderivative of x over x, the square root of x squared minus 1. So when I come back over to here, I get the limit as t goes to infinity of the square root of t squared minus 1 minus 1. And so the answer is infinity. And what we can say from there is that the integral from 2 to infinity of x over the square root of x squared minus 1 dx diverges. And that's example 5. Example 6. Suppose I give you the following. Suppose I give you the integral from negative infinity to infinity of x over x squared plus 1 dx. So this one's really good, okay? And what we're going to do is we're going to break this up into the integral from negative infinity to 0. Now, could I choose something other than 0? Yes. Could I have chosen 5? Yes. Could I choose 45? Yes. You just need a convenient number that's in between quote-unquote negative infinity and positive infinity. So I'm going to go like this. Now, let I1 equal the integral from 0 to infinity of x over x squared plus 1 dx. And I2 be the integral from negative infinity to 0 of x over x squared plus 1 dx. Now, so what that says is the integral from negative infinity to infinity of x over x squared plus 1 dx is I sub 1 plus I2. Okay? Now, if I could show that I1 diverges, I am finished. So there's no need to go any further because once one integral diverges, the whole thing diverges. And so let's come over here. So again, we're going to let I1 be the integral from 0 to infinity of x over x squared plus 1 dx. And so this is the limit as t goes to infinity of the integral from 0 to t of x over x squared plus 1 dx. This is the limit as t goes to infinity of 1/2 natural log of x squared plus 1 evaluated from 0 to t. So this is the limit as t goes to infinity of, in parentheses, or in these brackets, I have 1/2 natural log of t to the second plus 1. And then when I plug in 0, I get natural log of 1, which is 0, right? So I just get this, but that's infinity. And what that says is the integral from 0 to infinity, or I1, this diverges. And if that piece diverges, what we can say is the integral from negative infinity to infinity of x over x squared plus 1 dx diverges. So I know that's a mouthful, but you just need to prove that one of them diverges. Now, if that one happened to converge, you would have to check the other one. And that's how that works. So that was example 6. Let's do one more example for this video. So let's take a look at example 7. Suppose I had the following. Suppose I had the integral from negative 2 to 14 of 1 over, we're going to start to introduce this. So it's 1 over the 4th root of x plus 2 dx. So I want you to notice something. F of x, which is equal to 1 over the 4th root of x plus 2, has a discontinuity at x equal negative 2. So I'm going to take the integral from negative 2 to 14 of 1 over the 4th root of x plus 2 dx. So this is the limit as t goes to negative 2. Now, notice we're going from negative 2 to 14. So I'm approaching negative 2 from the right. Okay? And then we're going to take the integral from t to 14, right? So we have to replace the discontinuity with t because you don't want to be dividing by 0. So now, over here, we get 1 over the 4th root of x plus 2 dx. And this is the limit as t goes to negative 2 from the right of the integral from t to 14 of x plus 2 to the negative 1/4. dx. And so the way to integrate this is we take the limit as t goes to negative 2 from the right of, now we've done this before, we're going to get 4/3 of x plus 2 to the 3/4. Remember that negative 1/4 plus 1 is 3/4. Dividing by 3/4 is multiplying by 4/3. Evaluated from t to 14. And so this is the limit as t goes to negative 2 from the right of 4/3 times 14 plus 2 to the 3/4 minus 4/3 times t plus 2 to the 3/4. Now let's see if we can do this. As t goes to negative 2 from the right, this term drops off. It goes to 0. And over here, the 4th root of 16, here, let's just write this down first. So this is 4/3 times 16 to the 3/4. But I would think about it this way. So you're going to get 4/3 times the 4th root of 16 to the 3rd. The 4th root of 16 is 2. 2 to the 3rd is 8. 8 times 4 is 32. So we get 32/3. And so what that tells me, okay, is the integral from negative 2 to 14 of 1 over the 4th root of x plus 2 dx converges. And that'll conclude this video for section 7.8, where we did 7 examples of improper integrals. Thank you.